So francium silver is FrAg. Before sort of diving into the science, I just want to mention our collaboration. I'm here representing a large collaboration. I hope to do equal levels of disservice to everyone's hard work. I'll highlight first my main contribution to this collaboration is the name. So here with us today, we have Dave DeMille from Johns Hopkins and Mohit Verma from Chicago. Mohit has a poster, talk to him. Myself from Waterloo and Svetlana Kochakova from Temple and NIST, and she also has a poster here, so lots of folks to get more information out of. But it really is sort of a cross-border collaboration, no matter how fraught the border gets. So I wanted to give a bit of a maybe bigger thought on what we're doing when we're looking for CP violation with EDMs. What's the big question we're answering? And it's this baryon asymmetry problem. And in some sense, it's why are we here, right? There's a universe that has matter, though the standard model essentially predicts in the early universe we should have equal amounts of matter and antimatter. And that is more or less what we see. So I took a photo of the early universe here. Matter's black and antimatter's white. You see it's quite a uniformly gray photo. If you squint very hard, right there, you still won't see the difference, because the difference would be 1/100th of a pixel being just one step darker than medium. So this is an incredibly small asymmetry between matter and antimatter in the early universe, but that's, well, all the matter that we see, right? The scale bar here is in gigalight years, so galactic superclusters and things. All the matter in the universe comes from that tiny asymmetry. And we'd really like to know, where that comes from. So Sakharov gives these conditions for creating a baryon asymmetry. You have to violate baryon symmetry. That seems important. If B is going to be not zero, you need out of equilibrium physics. And then where we're all focusing for these EDM questions is on CP violation. And as Dave explained, so I will just flash past it, CP violation and T violation should be equivalent under the CPT symmetry, which is extraordinarily well verified and theoretically supported. And so if we have this sort of bump from a charge asymmetry that gives us an EDM, that violates T symmetry and CP symmetry. Now, I'll come back to the scheme for how we measure this with EDMs, but luckily, again, people have already talked about the basic idea. If we have magnetic and electric fields to align the electric dipole moment and the spin, and then we flip one, we should see levels shift relative to each other. That's sort of the big picture idea for how we take these measurements. Why francium silver? Masochism. So francium is a radioactive atom. The longest lived isotope has a 15-minute half-life. Silver almost looks like an alkali if you squint hard, an alkali with awful UV transitions. So why are we doing this to ourselves? Well, one is what's been talked about a lot, that the internal field of the molecule gives you a massive enhancement to the field you can apply to the nucleus when you're looking for this EDM. Francium actually has two isotopes with octupole deformations of slightly different characters. Each of them gives at least a factor of 100 enhancement to the nuclear shift moment you should see compared to something spherical like mercury. Ultracold gives at least a 10-second coherence time. As Dave mentioned, the very first nuclear coherence time measurement in a molecule was done in the lab next to the one where I did my postdoc. I know how little effort they put into that, and still multiple seconds of coherence time. Over a minute has been demonstrated for rotational state coherence times by Simon Cornish's group at Durham. So let's say 10 seconds, and we believe we can go much further in the long run. The first generation, we're expecting about a factor of 1,000 improvement compared to the CP violation sensitivity of the mercury experiment. And we believe, as Dave was showing on his plot that just keeps going into the peta-electron volts, that we can keep pushing that with more number and longer coherence times. There we go. So the plan. First, we make ultracold francium. Then we make ultracold silver. We put them together as to a stable mixture. Well, that's an old slide, sorry, not profit. We're going to make ultracold molecules from that mixture and then search for CP violation with them. So currently we're working, again, in a number of dimensions in such a large collaboration. At Triumph, we're working with francium that is produced by a nuclear accelerator. Triumph, if you don't know, is Canada's National Nuclear Physics Lab in Vancouver, in a lovely sort of little forest next to the city. Inside, it looks like that, which is very much not a tabletop scale. That's what's required to produce our francium, but there's a little hut in the back. Okay? And inside that little hut in the back, we huddle around and actually make magneto-optical traps of francium. The radiation signs I took this picture right after we did a beam time, so the lab gets a little hot in the radioactive sense during the beam time. But what's in there is not so dissimilar to a magneto-optical trap that you'd have in any normal atomic physics lab. There's an example of our little francium mott. So francium motts have been made for decades now. Luis Orozco started this experiment at Stony Brook, and then it was moved to Triumph about 15 years ago. The experiments that they were doing were all very focused on very particular measurements of parity violation in francium, and so there were a number of things they didn't care about, like density, atom number. So we took a beam time at the end of last year, measured those things to understand what it would take to do molecular spectroscopy in francium, because with laser cooling, our next step is to try to understand the scattering properties of the atoms. If we want to get ultra cold, we want to evaporatively cool, and that requires good scattering properties, or bad scattering properties and a plan for how to fix them. Okay? So the way to understand this is to do photoassociation spectroscopy. The idea here, where did that big stick go? That seemed useful. All right, there we are. So the idea here is we take our colliding atoms and we use a laser to drive them into an excited state. And as we change the frequency, when we find a molecular resonance, suddenly the number in the mott drops out. Knowing where these excited molecular states are allows us to do a 2-photon measurement, and we can essentially turn that loss process off when we find a ground molecular state. It turns out the scattering properties of two atoms with each other are very closely tied to the position of the least bound molecular level. And so we just want to, I will definitely trip over it if I do that. There we are. So we want to find those least bound molecular levels and then talk to theorists like Svetlana to be able to extract the scattering properties, both the scattering length and the positions of Feshbach resonances that we can use if the scattering length is not to our liking. So we did a preliminary run of this at the end of last year again, and part of the characterizing of density was realizing it really wasn't quite good enough in the mott that we had there to see these molecular resonances. So we're moving forward with this nice upgrade that's, well, it's hard to work in that confined space, and this is sort of the perspective of life. Everything is at a funny angle. But so now we're putting in an optical dipole trap, and so at the end of this month, I'll be back out there and we'll be doing experiments with optically trapped francium. So both allows us to get to higher densities and get to much lower loss rates. It turns out there's a lot of light-assisted loss in the francium mott. So we'll be looking for those molecular resonances so we can understand the scattering properties of francium to allow us to go all the way to nanokelvins with evaporative cooling. Okay. Ultracold silver is the next step, or I should say the parallel step. So this is ongoing work at Chicago, which will very soon be moving to Johns Hopkins, though hopefully not in 1 month, but maybe 3-4 months we'll be moving to Johns Hopkins. Silver was magneto-optically trapped once 20 years ago, and now a second time at Chicago. This is a nice picture of a silver dark spot mott. We get nice parameters for both number and density. Temperature is high, but the atomic structure of silver would make you think, yep, it's going to be hot. I always have to remember that when I say something less than a millikelvin is hot, that's a very field-specific perspective. All of my colleagues at the Institute for Quantum Computing have like dilution refrigerators and would love to have this temperature. But okay, we want to be colder than that. And so we moved to subdoppler cooling of silver, which had not been demonstrated in the past. With a blue-detuned, what's called gray molasses cooling scheme for silver, we're able to drop that 700 microkelvins down to just a shade under 90 microkelvins. And we believe with like improved beam balancing and efforts, we can actually bring this down at least a factor of 2-3 lower. But this is already quite cold, and you saw that our dark spot mott is quite dense, and so we have really ideal conditions to move on to scattering properties, but before that, this is cooling after trapping. We'd like to add a magnetic gradient to this and do, in fact, a blue detuned MOT, which has been demonstrated only with rubidium in terms of atoms. In fact, Mike did that. Where's Mike? Well done. And so in preparation for that, we've also done some experiments at my lab in Waterloo with cesium. I just want to show you a little video of a blue detuned MOT. What you'll see is first, a regular red detuned MOT turns on and oversaturates the camera. And then we switch to the blue MOT, and you'll see there's kind of a little dynamic for loading this thing. Also, my hand is shaky, sorry. There's a red MOT, and then whoop, and it kind of like swirls down into the blue MOT. So we've got experience making blue MOTs with at least one atom, and silver should be knocked off the list very soon. That will have us in really great position to look for these scattering properties. Same story with photoassociation as it is with francium. We look for these molecular levels, and then Svetlana's electronic structure calculations combined with that can tell us what to expect when we load silver into an optical trap. So once we have both of them ultra-cold, the next step is to merge them. We have already a design for a machine that will be able to merge francium and silver together for these purposes. And I just want to mention sort of this part up to that gate valve exists already at Chicago. This is where we're doing this silver laser cooling. And everything from this gate valve up also exists both at Triumph and in a second setup that we started building at Chicago and recently moved to Johns Hopkins for doing francium. Because while Triumph is a lovely place and a great source for francium, we have to apply for beam time. We get a little bit of the year for that. So we're building an offline source for francium. Okay? Now, that setup got very complicated. I made it bigger so you can see it bigger, but I'm not going to sit here long enough for you to take much away from it, other than we have a plan. We know the parts. We're thinking about the two chambers that aren't there yet and what goes into making that. But the offline francium source. So this exists up to, again, go pointing here. Below this gate valve, we're thinking about, and I'll get to that in a moment, everything above this gate valve exists. It turns out that francium and rubidium have their transitions at very similar frequencies. And so we can do everything we want to do to francium with rubidium and then just retune the laser, and it should work for francium. Now that should actually works out almost every time at Triumph, so we're happy with how that is. Recent highlight from this is an ion-loaded rubidium MOT. Now I said ion-loaded, let me back up for a moment and tell you why that matters. Francium at Triumph comes out of a cyclotron as a very high-speed ion. They slow it down, and it impacts into a surface that neutralizes it. Then that's here. That flips up. We heat it up. It releases some francium, and then we catch it in a MOT up there. Okay? So we've now done the same process with rubidium just to demonstrate all the ion optics is working. The funny silene coating you have to put on the glass cell from the MOT, that all works. So we can make a MOT in exactly that way. The only thing that's missing is the radioactive francium. That's an ongoing work with our collaborators from the University of Utah. Tara Marston is the PI there. And she's an expert in radiochemistry and working on how to electroplate the things we need. So francium only lives for 15 minutes. We can't just stick a chunk of francium in and hope for the best. So instead, we take actinium if we want to do one isotope of francium, thorium if we want to do the other, plate them onto a substrate. That then goes into an oven that produces the daughters that we want. It looks more photogenic when they actually build the cell for doing this. And so they've made great headway on understanding exactly what goes on when we try to plate actinium onto particular substrates like platinum and zirconium that are the ones we want for a whole host of technical reasons I can't possibly get into now, but there they are. The last thing about stable mixtures that I want to mention is if all the molecular spectroscopy tells us they won't be stable on their own, well, we can push them to be stable. And the way that we push them to be stable is with a Feshbach resonance. Okay? So Feshbach resonance is a way to tune the scattering properties of two atoms by tuning a magnetic field. Now, we haven't done the molecular spectroscopy, so the actual positions of these resonances are not actually something we can predict, but the kind of density and the rough shape of them we can. And in particular, this one here, from my experimentalist eye, it looks great. Got a good width, should be nice and stable. We can tune attractive interactions, repulsive interactions, strong, weak, however we'd like. So the system looks very promising for control into the future. That picture is going to make an immediate return because this next step of making molecules requires essentially two real steps of experiment. The first is Feshbach association. Okay, so the top of the plot is showing you what happens to scattering properties as a function of magnetic field. The bottom is showing the energies of molecular states versus magnetic field. And so this great big looking Feshbach resonance here is caused by a nice molecular level crossing zero energy. If we start at a slightly higher magnetic field with free atoms and we ramp the magnetic field down, we can coherently associate them into that molecular state. So we can go from atoms to molecules without producing entropy, which is a great thing to do. Now, that association efficiency sometimes is quite low. With sodium lithium that I used to work with, it was upsettingly low. But there are ways to make that efficiency higher and higher through technical advancements. Once that's happened, you've got an incredibly loosely bound molecule. That's not the kind of molecule that gives you this huge electric field enhancement. So the last step here is stirrup, which Mike already mentioned, stimulated Raman adiabatic passage. The idea here is that we start from this very weakly bound Feshbach molecule that looks more or less like the free atoms. And through a coherent two-photon process, we use an excited level as leverage, but we don't actually populate the excited level because it's unstable. And so we can move through there to the absolute ground state, which is a tightly bound, highly dipolar molecule. That's perfect for doing the CP violation search. So since I'm out of time, I'll just again say, there's the rough schematic for how we do this, looking for a nuclear spin flip whose frequency depends on the relative orientations of magnetic and electric fields. Amar stressed that systematics are really the thing that one has to worry about, and I'll just show one particular thing that we've been thinking about. Again, this is from Svetlana's structure calculations, thinking about the impact of the trapping light on the molecules and finding what's called a magic polarizability, or sorry, magic polarization, magic wavelengths. There are different ways to mitigate these effects, and we're working on those in parallel such that when we finally got these molecules, we can go ahead and make the measurement. And with that, I will just put up the sort of rogues gallery of the collaboration, and happy to answer questions.